So let me begin by thanking the organizers for giving me an opportunity to speak in this wonderful workshop. So I'm going to try to cover two topics, but if the second topic I will only do if I get time. So please stop me for questions because I feel that I might finish soon. So, okay, so the first part is Lyapunov Exponent and out-of-time order correlator in chaotic systems. So the subject of my talk falls under this field of quantum chaos. So one of the goals of quantum chaos as a field is to define what quantum chaos is, basically. What do you want to study in this subject? So there are a couple of motivations that are of interest. So one of the motivation is to find diagnostics and fingerprints of chaoticity in quantum systems. For example, as Leah pointed out yesterday, you can have Wigner-Dyson type statistics which corresponds to eigenstate chaos in quantum systems. But there is another motivation that kicked off this field in the late 70s and early 80s is that how does classical chaotic dynamics emerge out of underlying microscopic quantum systems? So this was the motivation that kicked off this field of quantum chaos. So most of the understanding of the microscopic world that we have over past several centuries is based on three pillars: classical regular dynamics, classical chaotic dynamics, and over the past century, quantum physics. So quantum physics emerged as a more fundamental law of nature, and whenever a more fundamental law replaces the existing theories, it should contain it as some limiting case. It should not completely invalidate it, but you should be able to take some small Planck's constant limit and then recover the classical dynamics that people are comfortable with. So as soon as quantum physics was developed, the first motivation was to develop correspondence principle by taking small h bar limit and recovering classical regular dynamics. On the classical realm, the similar program was developed for correspondence between classical regular and classical chaotic dynamics in the form of this very elegant mathematical framework of Kolmogorov-Arnold-Moser theory. And more recently, people have started asking this question: how does classical chaotic dynamics emerge out of this microscopic quantum dynamics? And basically, this is one of the key motivations that led to the field of quantum chaos. So it's basically developing a correspondence principle between classical chaotic dynamics and underlying microscopic quantum physics. And a historical overview is given in this very nice article by Martin Kurzwiller, who was a pioneer of this subject. So yeah, so let's recap the key question that I'm going to focus on this talk through various technical calculations that I'm going to show. How does chaotic classical dynamics emerge from quantum physics? So to address this question, I would consider the simplest possible model of chaotic system, the kicked rotor. So this kicked rotor was introduced by Chirikov et al. in 78. And it's a very simple model. So it's just like a particle on a ring, which is being periodically pulsed by a delta function potential at integer times in units of this time period. And if you want to write down the Hamiltonian of the system, is simply just the kinetic energy plus this delta function potential. So at time t equal to n, I have set the period capital T to 1. So at every integer times, it imparts this much potential onto the particle for that delta function pulse. So you can write down the equation of motion for this Hamiltonian, classical equations of motion for this Hamiltonian. And this gives rise to the well-known standard map. So the standard map is nothing but this Hamilton-Jacobi equations corresponding to this Hamiltonian, which is given in terms of these coupled discrete equations. The discrete nature of this equation comes from the fact that there is a delta function in this Hamiltonian. So let's, I will be making parameters dimensionless in the rest of my talk. So I have set everything to 1 and k is a dimensionless constant. So the only parameter in the standard map is the strength of this kicking, k. And let's look at the dynamics of this standard map. So to understand the dynamics of this standard map, what people generally do is to develop phase space portraits. It's a visual way of understanding the chaotic dynamics of a system like this. So how to generate this portrait for people who don't know, what you do is that you initiate your dynamics with some set of initial conditions. arbitrary number of initial conditions, and then just fill the phase space portrait with these initial conditions. And if the corresponding dynamics is confined to some regular trajectories in this phase space, then the system is regular, it's not chaotic. And that's what happens for small kicking strengths. So your particle, when it's kicked at very small values of this dimensionless kicking strength, it has a regular phase space structure. And as you slowly increase the kicking strength from k equal to 0.5 to let's say 0.97, which is a special value, it's a critical value. And you see that this phase space structure starts becoming more and more fuzzier. And the fuzziness is nothing but that the two neighboring infinitesimally separated initial conditions will give rise to very different dynamics, exponentially separated within this fuzzy region. And the more technical aspect of this is that this is a point at which the last Km orbit, Kolmogorov-Arnold-Moser orbit collapses. And then the system is entering chaotic region. And if you keep on increasing this kicking strength, then eventually what happens is that the phase space is completely filled up, it becomes completely chaotic, and then this is what the phase space looks like, except some set of measured zero regular orbits which are always present. That doesn't matter. So how to quantify the degree of chaoticity in these systems? So the degree of chaoticity can be defined as a ratio of distances of phase space, distance in this phase space at two different times. And if this, so d0 is some distance in this phase space region, and d of t is the same distance at time t. So if this distance has grown apart exponentially, the growth rate of that exponential term is what people call Lyapunov exponent, and this is what quantifies the degree of chaoticity in these systems. So let's quantize this standard map now. So the quantum version of this standard map is just given by the same Hamiltonian, but just replace the variables by operators now, living in a Hilbert space. So the first insights in this quantum version of standard map came via an ingenious mapping by Prange, Grempel, and Fishman, who just took this quantum Hamiltonian and through a sequences of very counterintuitive transformations, mapped this model onto a tight binding lattice with an on-site disorder potential. So this is not true disorder, but it's a quasi-random disorder potential. And this lattice is not in the real space, but it's in momentum space. And this is what is known as dynamical localization. This is Anderson localization, but it's happening in momentum space lattice. So what the consequence of this statement is that the chaotic dynamics that you would expect in the quantum regime is localized in momentum space. And this suppression of chaos in quantum regime is via Anderson mechanism. So the Anderson mechanism is the route through which deep in quantum limit, quantum interference effect suppresses this chaotic dynamics. And notice that now there are two parameters in this quantum regime. In addition to this classical parameter k, which is the kicking strength, you have the dimensionless Planck's constant. Sorry? Oh, sorry. So alpha is basically whatever is sitting in front of p square, some h bar dependent variable. Which k? Oh, k is in this WM. Yeah, it's in this hopping. Yeah, so you can fine tune this to be a nearest neighbor also. So it's your choice. And yeah, so you can play with this to get a nearest neighbor hopping. But this is the general mapping. So you can get a nearest neighbor with this tan potential. But this is in your hands. How you kick your system is basically in your hands. So you can design whatever you want. And alpha is this incommensurate. So why this is quasi-random? So there is a lattice periodicity due to the discrete nature of this U of R. So there is one period. And then this on-site tan potential which superimposes this lattice periodicity is incommensurate with respect to this underlying lattice period. And hence the quasi-random design. So as soon as you have this, so the H effective is sitting inside alpha. So as soon as you set this H effective incommensurate with respect to the underlying lattice period, it's a disordered Anderson problem and everything is localized. So that's how, so this mapping is like, you can do a step-by-step mathematical transformation to get to this point. No, it's just like identity. So you do some transformation, you apply some transformation on this Hamiltonian and then you get this lattice. There is no argument. Actually, you don't need to have irrational. You can have, yeah, it's an irrational with respect to the underlying lattice periodicity. Actually, the thing is that there is an H effective here. So there is an H bar sitting there. So you can set H bar to, let's say, 1, which is H is 2 pi, and then you can, so this 2 pi is incommensurate with respect to this lattice period 1. So that's how it appears. And you want to be like that because otherwise there are spurious resonances that will dominate your system. So this, setting it rational doesn't, it hides the physics that you are after. Okay. So let's start to recover some, do this program of recovering classical physics from this quantum kicked rotor problem. So you have to recover it one property at a time. So let's look at this diffusion, the simplest thing that you understand, diffusion, which is nothing but the average kinetic energy, E square. So if you plot this average kinetic energy as a function of time, which is just the number of kicks that you are giving to your system, the classical kicked rotor is just diffuses linearly in time, which is just the expression for classical diffusion. But if you do a quantum mechanical calculation at early times, short times, it starts overlapping with this classical linear behavior. But then at some time, it starts to deviate from this classical behavior, and then it's suppressed at later times. So this suppression is what is called dynamical localization. Yeah, sorry. So this is the quantum mechanical Hamiltonian. I want you to focus. In the transformed Hamiltonian, it's inside the W. Means I just kept it a general form. Means I think I should not have written K. I just V of theta basically, which has K inside it. Then that K is equal to 0 is just free particle. Yeah, it's integrable. Yeah, it's a difference relation. But these are the eigenvectors, elements of eigenvectors. It's a tight binding model. Yeah. So then you see that this at late times the quantum version of this model has suppressed diffusion, and this is what dynamical localization. And the Anderson insulator mapping exists somewhere in the late time behavior of this model. At the point when it departs from this linear behavior, is given by what is called weak localization physics, where first quantum interference effect starts kicking into your system. And this is much more richer physics than just the Anderson insulator mapping. The Anderson insulator mapping sits somewhere here, but then this is more involved physics of weak localization. And this has been seen in experiments in as early as 1995, where similar behavior of linear and departing from this linear behavior was observed in this atom optics. And then since then, there are several experiments that I don't even want to mention because there's too many experiments on this. Okay. So diffusion is one of the properties that we establish correspondence principle to. So the next thing is that since we introduced Lyapunov exponent, so what happens to Lyapunov exponent? So let's define Lyapunov exponent, how people calculate, yeah. Sure. Yeah, linearly. Yeah. Yeah, because it's that's what dynamical look. Yeah, it's basically Anderson localization in momentum space. So the U's that you are here are momentum space points, basically. So then if they are localized at momentum space, they are not heating up to infinite temperature. But classically, it just keeps heating up because it continues to absorb energy from the system and then transfers to the rest of the at later. Okay, so let's define a more formal definition of Lyapunov exponent. So the Lyapunov exponent, when people working in classical physics calculate Lyapunov exponent, they use this formula. So what they do is that they take this distance ratio I defined in the previous slide, take a logarithm, divide by t, that's lambda basically. And then take this limit of initial trajectory separation going to 0, such that you always start with infinitesimal trajectory separation, and then take long time limit, and then do a phase space average. So for subtlety that I will come to later, I want to call this lambda classical. And this is the formal definition of Lyapunov exponent. And you can linearize your standard map according to Chirikov's method, and then this lambda classical has this following estimate, log k by 2. The k is the kicking strength. And this estimate holds for k greater than 4. Yeah. No, it's mod 2 pi, right? Everything, it's a compact phase space. Yeah. So it's the particle on. Yeah, so you can get a more nastier formula which works for all k, but I won't be writing it here. So the question is that can we extract some Lyapunov exponent-like object by going to the semi-classical limit of a quantum kick rotor? So this has, even though this model has been studied to death in literature, it has not been executed so far. So because one of the reasons, so this question hides some fundamental subtlety of quantum mechanics. That Lyapunov exponent is inherently a trajectory property of the classical trajectories. But in quantum mechanics, uncertainty principle forbids you from simultaneously defining position and momentum, which is a key property of your trajectory. So how do you even define this object in a quantum sense was the main reason that people could not extract something like this. So to avoid this, yeah. So you can start your, initialize your system at various x0, p0s. So because I have taken t going to infinity, so the time is a long time expression. So now time is gone, so now you can average over phase space. It is an average over initial states. Some random collection of x and p's basically, which means all possible x and p's that you can humanly define in your numerics, let's say. So that's how you generate the phase space portrait in the first place, right? You generate all possible initial conditions and see how the trajectories evolve with that. So then once you have your phase space portrait, you can take this long time limit and then just average over it for all possible points on that phase space. So look at the quantity that I'm defining is the separation between two trajectories, right? So P keeps growing, but I'm not defining, the D is like distance between the two trajectories. So, and D0 going to 0 limit is what keeps these two trajectories infinitesimally separated. And then if I separate it, so okay, so actually this leads to a numerical subtlety that people do. So if you start from two nearby points, so the trajectory diverges like this, let's say, exponentially separates out. But if you keep following that trajectory, it's not exponential separation anymore. It's only exponential separation up to some points in the trajectory. So what you do is that you reset it to some different infinitesimally separated trajectory. So that's the limit D0 going to 0 does for you. So it's a formal technical point actually. Yeah, but if you just follow one trajectory, you will lose this exponential separation. Yeah, so this is the definition of D. So this is like x prime, which is a neighboring trajectory, and this is x, which is, there are two trajectories involved here within D. Yeah, so that defines the distance in the phase space. Okay, so in order to extract something like a Lyapunov exponent, so we make use of this recent interest observable out of time order 4-point correlator. Actually, it's not quite new, this object. So this was initially introduced by Larkin and Ovchinnikov as early as 1967. So the motivation of Larkin and Ovchinnikov to study this object was to understand how far you can push the semi-classical approximation in a disordered superconductor. So the motivation was that this object, the out-of-time order 4-point correlator, pushes the limit, tells you how far you can reliably trust your semi-classical approximation. So the semi-classical approximation is just where you naively replace your commutator with a Poisson bracket and get away with it. So what they showed is that if you just look at your 2-point functions, then semi-classical limit has no breakdown. You can always use semi-classical limit as much as you can. But if you look at this out-of-time order 4-point function, the Poisson bracket and the commutator coincides up to a time scale which is called the Ehrenfest time scale. And post this Ehrenfest time scale, this Poisson bracket does not match this commutator. And then you have to do full quantum dynamics to extract an object like this out-of-time order 4-point function. So this is what distinguishes how far you can reliably, it tells you the boundaries of semi-classical approximation and beyond which you cannot escape from computing the full quantum dynamics of your system. Yeah. No, actually semi-classically you do Poisson bracket thing, but then you do an operator expectation like that. So with respect to your some packet, wave packet that you have prepared. So if you start your wave packet, it spreads, right, as your time evolves. Yeah, exactly. You do all these tricks to write down this proper Wigner function, which takes you from one regime to another regime. Yeah, there are some subtleties involved how to do it correctly. Yeah, and then further, Aligner and Larkin established this Ehrenfest timescale for this disordered systems to be of the order of log h bar. And this was done using this weak localization theory. So let me define what this out-of-time order correlator means physically. So what it means is that it's a two local operators for our purposes, W at time t and V of 0 and commutator square, and then it's a operator expectation, quantum mechanical expectation. So what you do is that at time t equal to 0, you insert a perturbation V, and then you let it evolve till time t, where you insert another perturbation W of t, and then you turn back. And then when you turn back to time t equal to 0, then if system is not at all chaotic, then you should recover your V of 0 back. But if your system is chaotic, depending on the degree of chaoticity in your system, you won't be able to recover V of 0. And this object just quantifies how much you have not recovered once you turn your time back. And this is what this object quantifies. So this is some sense capturing the sensitivity to initial conditions by coming back to your original system and see how much. It's closely related to fidelity, but it's still a bit different. And there is some difference between this object and Loschmidt echo also. So the to and fro evolution is with the same Hamiltonian, but in Loschmidt echo, you modify your Hamiltonian at time t before turning back. So that's the key difference between these two diagnostics, and it cannot be interchanged. Okay, so let's see what are the features of this out-of-time order correlator. So there are two time scale associated with this. One is this thermal time scale, which is just given by your mean free path, and the mean free path can be replaced by this classical Lyapunov exponent. So that's the initial time scale. So this is the time scale at which all your 2-point functions saturate. And then post this time scale, your 4-point function, just at the point where your 2-point functions saturate, your 4-point starts taking off. It starts, so if you initiate this object, then it off commutes with more and more. Yeah. I will apply this for kicked rotor, and then I will give a specific example. For now, it's like some local operator. I don't want it to be a projector on the system. So I wanted to let it spread in a sense of not commuting with more and more regions in your system. So then it starts taking off at this time scale, and then exponentially grows if the system is chaotic. And then it's at Ehrenfest time scale, this growth saturates. So the recent result by Shankar Stanford and Maldacena is, which is the paper title Bound on Chaos, puts a bound on the rate of growth of this exponential. And this exponential, this bound is between these two time scales, and just given by, for a thermal system, it's given by 2 pi kBt by h bar. Yeah. It can be power law actually. Then it depends, system dependent thing that happens. So there, yeah. So for example, if you have a purely quantum mechanical system like spin halves, there is no exponential growth because there is no Ehrenfest time scale. Spin half is inherently completely quantum mechanical to start with. So means this bound tells you that it is 0. Yeah, it is definitely not exponential. Yeah. Okay. So then these are the two time scales, and this is log h bar derived by Aligner and Larkin. And I want to remark that this h bar, so you have to create a separation between these two time scales to observe this exponential growth. It's not obvious that these two time scales are separated. You have to go to a regime in which these two time scales are well separated. So then what you see is that you have to take h bar to be very small in order to push T Ehrenfest much larger than TD. And so this scale separation is achieved in the small h bar limit, which is the semi-classical limit. And notice that this small h bar is same as large n for many body systems like the Sachdev-Yekitai models in the following sense. So when you do your phase space, so all the kicked rotor type systems have phase space. So when you have a quantum system, then the phase space are quantized in packets of, in units of 1 over h bar. So when h bar goes to small, the number of phase space cells grow. And then this large number of phase space cells is equivalent to the number of many body degrees of freedom in this system. So there is a correspondence between this h bar in the simple kicked rotor type systems and n in the many body systems like the Sachdev-Yekitai model. So if you want to estimate an Ehrenfest time in a many body system, then you use n, but for kicked rotor type system, it's effective h bar. Okay, so let's compute this out of time order correlator for this quantum kicked rotor. Let's specialize this diagnostic for this case. So then what you want to do is that the basic thing you want to do is that you want to compute the wave function evolution from t to t plus 1 after 1 kick. And this is done by acting it by an evolution operator. And notice that this evolution operator is factorized in this kinetic part and the potential part because there was a delta function. If it's not a delta function, you cannot factorize it and you have to put a time order here. But then the delta function makes the life simple. So then let's compute this two objects, which is 2-point function, which estimates the thermal time scale, TD, and then this 4-point function. And then the only operator that I have to substitute in the C of t is P of t and P of 0. So this is an example of a local operator that you can choose for kick. It's just the momentum operator. Sorry? Initial state is you can choose a packet, prepared wave packet, and then it's in your hands, basically. Actually, you don't want to have it too spread out, because the physics, underlying physics is that you want to let it spread as your quantum dynamics develops in your system. If you do a flat line, then it's not going to show you this physics. Completely spread out. You want to let it completely spread out. That's another way of looking at this. So then what you see is that, as I mentioned, that there is a catch-22 between this h bar and k, because you want to create this separation. So if you can choose as small an h bar that is possible in your numerics, which is like 2 to the power minus 14 that we could do. And k cannot be too large. So if k is too large, then this Ehrenfest time goes smaller. So, and then this window collapses. You want to have as much time window between the Ehrenfest time and the thermal time. And you have to choose values that are opening this window as much as you can. And these are the set of values for k that we have chosen, and this is the value of h effective. And you can estimate, plugging these values, you can estimate these two time scales. And the TD is basically less than 1 kick for these numbers. So the thermal time scale is always less than 1 kick. So it's not in your observable numerics. So, but if you plug in H effective and this, then these dashed lines are the Ehrenfest times corresponding to these different values of K. And then you see that if you compute the C of T, the out of time order correlator given by this object, it's in log linear plot. So it's a straight line means it has an exponential. So it grows exponentially up to this Ehrenfest time scale, and then it slows down. The exponential is changed at precisely at this time scale, and it coincides with these estimates of this time scale. And then you see that the B of T is basically saturated even before 1 kick, because the estimated TD is less than 1. And our times available to us are 0, 1, 2, discretized in integers. And yeah, so this is the exponential growth. Let's see how quantify this even more. So what I've plotted here is that the log of C of T divided by T. This is the growth rate, lambda, that I'm plotting in this log scale, and then the time is in the log scale. So the colors, different colors are basically different values of K, the kicking strength. And the insert is fixing K for 4 and then changing the H effective. So let's look at the different Ks and fixed H effective first. So what you see is that this log C of T by T is constant up to this Ehrenfest time scale, and then that means that there is an exponential growth up to some time scale, and then it's sharply subdued post Ehrenfest time scale. This is where the first quantum interference effect starts hitting the system. And then eventually it continues to slow down, and it means long time dynamics is outside the scope of the numerics, but it continues to slow down and it reaches T to the power minus 1 around 100 gigs. So what happens is that you have a constant lambda, the correlator growth rate, up to some time scale, and then this lambda becomes time dependent once the quantum effect starts developing in the system. And notice that another thing, if you fix K and change H effective, the value of this lambda does not change. The only thing that changes is the Ehrenfest scale. So if you plug in different values of H effective, if you increase your H effective, then basically you are decreasing the Ehrenfest time scale. It's closing down towards this. And then what you see is that it's the same lambda, but only appears up to some smaller time scale, because you have pushed your Ehrenfest time scale to smaller values by doing this. So the lambda is basically H effective independent. Yeah. Yeah, that's a good question. This was our initial motivation, but then we quickly realized that what you can do is look at the microstates. So every microstate may have its own temperature, but what happens is that it's like an infinite temperature state here. So any microstate will give you the same value. Yeah, exactly. Yeah, so yeah, that's the statement that I made. If it was H bar dependent, suppose, then it would give you different temperature at different microstates, and then you can probe this bound. That was our initial motivation. But yeah, but you have to look at some different models. But this model has this aspect. Okay, so and then what happens is at this point when this horizontal line takes a dive is where the weak localization starts coming into picture. And this OTOC growth rate post RNA slows down due to this quantum interference. And this diagnostic is like very powerful to bring out this physics at the level of Lyapunov exponent. So that's the key thing. So it's not so all the papers discussed this physics at the level of diffusion, but it's at the level of 1-point function, but I'm discussing this same physics at the level of out of time order 4-point function, which gives you the Lyapunov exponent. It's looking the classical to quantum crossover in terms of Lyapunov-like exponent. So next slide, I'm going to show that there are subtle differences between classical and this correlator growth rate. So let's compare this exponent that we have extracted from this out of time order correlation. And so what I'm plotting is there are 4 objects that are plotted in this graph. So one is this classical lambda that I defined. and the classical estimate, or Chirikov's estimate of this, the quantum out-of-time autocorrelator. So the additional thing I'm plotting here in addition to this thing is that I'm naively replacing this commutator by Poisson bracket and averaging over phase space. And that I call C classical. So the reason I'm doing this will become clear soon. Notice that these two expressions on the face value, there is a huge difference between these two expressions. So the difference is that you have, in this case, you have first taken the log of the exponential divided by t and then averaged it. But this expression is first you are averaging it and then taking the log. So what is happening is that if there is so the Lyapunov exponent, or this, if you have a phase space portrait, you have one lambda for each point of this phase space. There are various lambdas. There is no one lambda. There are various lambdas that you have to average over. So if you are averaging over the exponential, then the largest exponential wins. And then you see that even if your system is chaotic is in only this region and it's regular everywhere else, then this C of t will still give you exponential rise, because the largest exponent corresponding to this will win, and then rest of them drop out, and then you average it, you will get an exponential rise corresponding to this local chaotic phase space region. But this is different. So the classical estimate is first you take the log and then average over lambdas. So lambdas can be plus and minus, and then this diagnoses the global chaos of the phase space portrait. So the OTOC diagnoses local phase space chaos, and the bound that Shankar Stanford and Maldacena put is on the local phase space chaoticity of your system. So this is a very crucial difference, because these two averages does not commute in typical systems. And then now you plot this, what I'm plotting is lambda classical, lambda from this, lambda from all these expressions. And then you see that the green curve, which is the C classical, exponent extracted from C classical, completely overlaps the exponent extracted from the full quantum OTOC. This is excellent agreement all the way up to this large K. But then the lambda classical is suppressed compared to these two things. So this is an indication that these two things, what people call Lyapunov exponent in this nonlinear dynamics, is already quite different from what you have in this OTOC growth. Yeah. That's important actually. Okay, so yeah, so this is a key difference actually, and it can be important depending on which problem you are looking at. And fortunately, this simple model is able to verify these key differences. So one should not call the growth rate of this exponent a Lyapunov exponent. If you define Lyapunov, I think I have 20 seconds, so I think I will stop here. So I will just summarize. So using OTOC, we extracted Lyapunov exponent, a key fingerprint of chaos in quantum calculation of kicked rotor. We qualitatively understand the difference between the OTOC growth rate and classical Lyapunov exponent. It's a very important difference. So in future, we would like to extend this analysis to static chaotic systems. The static chaotic systems like stadium billiards problem, where you can actually add temperature. And so this is work in progress currently that we are trying to understand. And there you can have hopes to probe this bound, because here there was a dynamical localization post-Ehrenfest time, but in stadium billiards problem, it has Wigner-Dyson type statistics. So it would be interesting to see how this exponential growth morphs into some system with eigenstate chaos. So it might give you different exponent depending on, it might be h bar dependent exponential growth post-Ehrenfest time in these static systems without dynamical localization. So we want to remove dynamical localization from this picture, because that's kind of a nuisance, because in SYK type models, it grows exponentially deep in the quantum regime. We want to see the simplest model where you can have h bar dependent Lyapunov exponent if possible. And one long-term direction is that you can try to extract this exponential growth of OTOC from effective field theory of quantum kicked rotor a la Artland Zinbauer in 98. But one key difference is that you have to, this secretly employs Keldysh techniques, And out of time order 4-point functions are outside this Keldysh field theory thing. So you have to expand your Keldysh-Green's function, Keldysh contour by an augmented contour, and then carry out this analysis in this modified contour. And that, we hope that will give you an analytical insight of this exponential to linear growth of these out of time order 4-point functions. Thank you.
Are there more questions?
System, I mean, so did you say that, I mean, so if you start with wave packet and then at some point it, in phase time scales it spreads. Yeah. So, but beyond that, you don't expect to see the Lyapunov growth, right? I mean, the exponential growth.
You know, this is a bit murky point. This is what we are battling at this point on this billiards problem. See, the thing is that you have a semi-classical diagnostic for chaos, which is this exponential growth. But then post-Ehrenfest time, there is this eigenstate chaos that sets in this billiards problem. Means not post, but there is this Wigner-Dyson statistics in this levels of this quantum billiards, right? Yeah, single particle, but it has Wigner-Dyson. You can add some noise and then it has some Wigner-Dyson statistics. So in SYK, Shasdev-Kitaev type models, the Wigner-Dyson corresponds to the exponential growth of this out-of-time order correlation. So we are trying to put this picture together in this system. So there is an exponential growth in billiards corresponding to this classical Lyapunov behavior. But when you build this quantum effects, it's still chaotic in the quantum sense. So we are trying to see if you can unify these two diagnostics using OTOC. So this is a bit murky at this point. What will happen? So let's say if it doesn't grow exponentially, we think that it starts oscillating in some weird way, which we don't understand yet. Maybe we are making some mistake. It's still in progress. But we should be able to extract the fact that you have Wigner-Dyson out of this diagnostic somehow. Some feature of this diagnostic post-Ehrenfest time should tell us that we have a Wigner-Dyson distribution in this billiard problem. And how it manifests, whether it still continues to grow exponentially, but H-bar dependent exponential Lyapunov, we don't know.
Hello. So this Ehrenfest time is something very quantum, right? I mean, but then you showed that if you replace that by commutators, you can even get something similar out of
before Ehrenfest time. So the exponential growth is only between TD and TE, which is the Ehrenfest time. So I'm replacing this Poisson bracket, commutator with Poisson bracket before that time. After that time, I cannot do a reliable calculation. That's what Larkin.
But that Lyapunov exponent, which is like Lyapunov exponent like exponent, is defined within that time window only, right?
Yeah. That's where the exponential growth takes place.
And then we essentially, one could have described the classical system using that also from your calculations. Like,
yeah, that's the conclusion. Yeah, but then the new thing that you can do is that you can continue this diagnostic and see how this exponential changes to a power law and see the classical to quantum crossover, which will be absent in Poisson bracket. Because post that thing, the Poisson bracket breaks down.
Is where the 4-point has saturated. So is there like a hierarchy? If I look at higher correlators, like a 6-point correlator, then does that increase exponentially beyond TN saturate somewhere? And you have a hierarchy of these
time scales in this problem. If you look at higher, that's a good question.
I mean, are there other time scales?
Yeah, I don't know. What can it be actually? I wonder.
Sorry?
What can it be actually?
I don't know.
So it's a good question actually. You have to. It's a bit tricky to do those higher correlator calculations.
Meaning that, I mean, yeah, so I guess maybe the other time scales would also be set by the same parameters. It's, yeah, but I guess you need a large separation of time scales for this thing to work.
Means if we find something, I'm highly skeptical that we will have a new time scale there, but if it is, then it's a very fundamental quantum phenomenon.
So this localization in the momentum space, is this something generic that happens to classical systems when you classical chaotic systems when you do the quantization, or is this a very accidental?
Not quite actually, because in the static models, the stadium billiards model, there is no dynamical localization. So
when you do the quantization, when you do the quantization,
yeah.
Right?
So this is a peculiar property that there are two periods in this system, which are fundamental periods. So then once you go to this quantum system, these two periods are incommensurate, and that acts as a disorder and localizes it in the momentum space. So if you don't, it's a property of this dynamical system. But then if you have a static system, you have to by hand add some disorder to localize things. It will not happen automatically. So if you have a clean stadium billiards type problem of chaotic systems, then there won't be a dynamical localization.
Is it obvious that this is a time scale where semi-classical description breaks down?
That's what
It's not.
means. In Larkin-Ovchennikov paper, that's what their conclusion is actually. So
But in general, I don't think it's.
I don't know how generic it is. They were focusing on this dirty superconductors. And,
Yeah, because maybe in their case, so immediately once you reach the boundary, this interference kicks in. But if you think about, I don't know, some many particle system, like same system as interactions.
yeah, so if you have an SYK type model in mind, yes, it may work differently, but it's a tricky question actually. Means that's why we are doing this survey model by model to put together a bigger picture.
Yeah, that's a good point. And actually, it's known that if you do a semi-classical simulation numerically, you can go well beyond the arithmetic time and still get good agreement.
Not for this object. So that's the key point. So if you,
Maybe not for that object, but
that's
for,
my point.
But
That's
for,
my only statement.
Yeah.
So I'm okay. I don't know if I was clear about this. The Larkin-Ovchennikov paper talks about only that object breaking down post-errant system. So,
But if you talk more generally,
two-point functions, it's very well defined.
At semi-classical dynamics, you can do all.
Yeah. So if you want to look at the limits of your semi-classical approximation in a full dynamical sense, this is the patient zero to diagnose where your semi-classical physics breaks down for that object. That means you're missing something. If you're missing something that you are interested in or not, that's a different question.
Any other? Okay, so let's thank Ganeshan and all the speakers from the